Next, we want to do some referential integrity validation. Now, that's not a feature that Cassandra supports natively. You can have a table that refers to another table. That's easy enough to do. But the database itself is never going to tell you you're pointing to the wrong thing, or you're pointing to something that doesn't exist, or anything like that. So we'd like to solve that problem here. In particular, we'd like to know, does any of our playlists contain a movie that doesn't really exist? Let's look at the code for getting that done. First, we're going to create a playlists RDD. Easy enough. We get all of the playlists by user, and we're doing a slightly more sophisticated method here of turning that into a pair RDD by calling key_by. And we're picking out the movie ID as a UUID to make that the key. Likewise with movies, we get all of the movies, just select the movie ID, and key_by with that movie ID. Now that's a pair RDD where effectively there is no value, but that's fine for us. We just want the RDD to contain a complete collection of all of the valid movies. Now we want the result to contain playlists that don't have a valid join key. So this is going to call for a left outer join. We're going to left outer join movies onto playlists, as you see in that third line of code there, the third section of code, to keep only those tuples, those rows, where the second component is not defined. That is, where there is no valid movie associated with that playlist entry. Then we'll map those, since we have this nice polite pair RDD that contains a collection of the playlist row and the movie row. We really only care about the playlist row. So we're going to map that and pluck out the playlist row and make that our new result RDD, which finally we'll collect and iterate over and print out, and we'll show you just one row of that. That, you'll notice, is a Cassandra row at that point. This is no longer a pair RDD. After the map call in the left inner join sequence, that stopped being a pair RDD, and it's just now a collection of Cassandra rows. But we've got those rows, and we can now say, hey, here's a playlist entry that points to something that doesn't really exist. We can decide what we want to do with that. Do we want to delete it? Do we want to flag it? Do we want to put it in a queue and mention it to the user? All decisions the application can make, but we've done distributed referential integrity checking with this left outer join. Now we have the set-oriented pair RDD transformations. These are union, intersection, and difference. You see those Venn diagrams there. If you're not familiar with those as set terms, those very helpfully illustrate what these three things do. They are quite easy to call. We'll still show you some code and some examples of useful things we might do with these. If you really want to watch these work, you can type this code in. All of the examples are based on parallelized collection literals. So this is stuff you can play with in the Spark shell really easily. A key-based union is going to take those two arrays, and it's really easiest to visualize them in terms of the tables, the RDDs you see down below, but it's going to combine them. It's going to take anything that's in the first one, anything that's in the second one, and give us an output RDD that contains all of that, and yes, duplicates are allowed. If you want a key-based intersection, it turns out you have to do a little bit of this work on your own. This is an important set operation that takes two RDDs as input and gives you an output containing the keys that are common to both. However, unlike a join, it doesn't do any sort of collection or aggregation of the values. You're still going to get one record in the output RDD per record in the input RDD. You don't get iterables of the values that you saw on the inputs. So looking at the slide, we see we have to do a little bit of work. First, we're going to take that RDD A, group it by key, and join it to B grouped by key. That's really what a key-based intersection is a join. However, at the end, we'll flat map the results. We'll flat map the values and unroll the collections that the join created for us. Key-based difference, also fairly straightforward. It takes a second RDD and finds all of the occurrences of those keys in the first RDD and strips them out. So you get only keys in the first RDD that didn't happen in the second one. And as you can see in the example here, K1, K2, K1, and K3 occur in the first RDD. The second has K1, K2, and K4. K3 is the only one that escapes the notice of that second RDD, and it's what occurs in the output. We can actually use that to do a simplified bit of data validation. A little while ago, we found all of the playlists that didn't have valid movies. We used a left inner join for that. We can actually do that with subtract by key. Let's take a look at the code. First, we get the playlists from the database. We turn them into a pair RDD based on movie ID. Then we get the movies, and we turn them into a pair RDD based on movie ID. Again, kind of that silly pair RDD in the movie example, because there is no value, but that's okay, that's all we need. Then we take the playlists and subtract the movies by value. Collect for each, and you're done. It's a much simpler way to think of it in terms of a set difference than the inner join logic that we wrote before. So you can see that the mere fact of breaking up an RDD into a key value structure exposes all kinds of powerful functionality and a few really useful APIs that address very practical use cases that we can apply even to our fictional video hosting website. This stuff is super useful, and I hope you've gotten a feel for how pair RDDs can unlock a lot of the power of Spark.